For 50 years, astronomers believed they understood where black holes belong, locked at the center of their galaxies, anchored, permanent. They may have been wrong. In an old Hubble photograph, astronomers spotted something strange in deep space, a razor-thin streak of light, 200,000 light-years long, pointing back at a galaxy that appears to be missing its central black hole. Which means something with the mass of 20 million suns may be loose between the galaxies right now. And if that is true, it raises some troubling questions. What could throw a supermassive black hole out of its own galaxy? Where is it going? And how many more are out there invisible, silent, and running that we have never seen? So let's start with what we actually know. The streak is real. That much was settled quickly. Once cosmic rays were ruled out, the feature remained in the data a long, thin, almost perfectly straight line, connected at one end to a small, compact galaxy. Now, when astronomers find something they can't identify in an image, the next step is always the same. You point a bigger instrument at it, and you break its light apart into a spectrum. A spectrum is like a fingerprint. It tells you what something is made of, how hot it is, and how fast it's moving. Because the streak was so weird, Van Dockum and his team booked follow-up time at the WM. Keck Observatory in Hawaii, home to two 10-meter telescopes that are among the most scientifically productive on Earth, sitting on the summit of Mauna Kea. And the instruments they used have a pedigree. One of them, the low-resolution imaging spectrometer, was built at the California Institute of Technology and commissioned back in 1993. It's an ultra-sensitive workhorse that can record the spectra of up to 50 objects at once, and it was used by the astronomers who won the Nobel Prize in Physics in 2011, the team whose research determined that the expansion of the universe is speeding up. The other, the near-infrared echelon spectrograph, came online in 2018, and it specializes in extremely faint red objects at the far edge of what we can see: brown dwarfs, quasars, and galaxies from the earliest times in the universe. In other words, the mystery streak was now being examined by instruments that had already helped rewrite cosmology once before. Van Dockum would later describe what they found as quite astonishing, very, very bright, and very unusual. The spectroscopy revealed that the streak was not a smudge, and not a trick of the light. It was a chain of young, hot, blue stars, newborn stars. And the chain was enormous, 200,000 light-years long. For a sense of scale here, our entire Milky Way galaxy, every star you have ever seen in the night sky, and hundreds of billions more, is about 100,000 light-years across. This single thread of stars was twice that, twice the diameter of our entire galaxy, drawn across the darkness like a line of chalk. And the light from this object is old, very old. The galaxy it connects to is so far away that its light took about 7.6 billion years to reach Earth, which means the image Hubble captured is a snapshot of the universe when it was roughly half its current age. Here's the part that made everyone lean in closer. The streak wasn't faint compared to its surroundings. It was almost half as bright as the galaxy it was attached to. A thin line, glowing with nearly half the light of an entire galaxy. That kind of brightness means one thing. The trail must be packed with an abundance of brand new stars. Van Dockum called the discovery pure serendipity. He wasn't searching for it. Nobody was searching for it, because nobody knew such a thing could exist. One of his graduate students, Imad Pasha, described the journey from noticing the streak and thinking, "Hey, that's weird," to publishing a scientific paper as incredibly fun and satisfying because the entire team was learning every step of the way. That's worth sitting with for a moment. These are professional astronomers, people who study galaxies for a living, and they were learning as they went because the universe had just handed them something that wasn't in any textbook. So what was it? At the very tip of the streak at the far end, Out in the emptiness beyond the galaxy, the Keck data showed a remarkably bright knot of glowing ionized gas. Something was there, something compact, something energetic, and something moving. When the team worked through the data, they arrived at a candidate explanation. And it is the kind of explanation that sounds like science fiction until you check the math. A supermassive black hole, weighing as much as 20 million suns, thrown out of its own galaxy and running. Let that sit for a second. Black holes are famous for staying put. A supermassive black hole is the anchor of a galaxy, the single heaviest object in it, resting at the exact center, with billions of stars turning around it. It is, quite literally, the last thing in the universe you would expect to find out on its own, in the middle of nowhere. And yet the data pointed to exactly that. Based on the observations, this black hole had been hurtling through space at about 4 million miles per hour, and it had been doing so for the past 39 million years. Now, 4 million miles per hour is a number too large to feel. So here's a comparison. If this object were inside our solar system, it could travel from the Earth to the Moon in about 14 minutes. 14 minutes. The Apollo astronauts needed days. And this isn't a pebble moving at that speed. It's an invisible object with the mass of 20 million suns plowing through intergalactic space. NASA's own description of it was blunt, an invisible monster on the loose. But here's the strange part, and this is the detail that separates this object from anything seen before. The black hole isn't eating. You might expect a black hole barreling through space to devour the stars ahead of it, like a cosmic Pac-Man. That's not what's happening. It is moving far too fast to stop for a snack. Instead, it's doing something no one had ever observed. It is plowing into the thin gas in front of it, compressing it, and that compression is triggering the birth of new stars along a narrow corridor behind it. In other words, the streak in the Hubble image is not debris, it's not wreckage. It's a trail of newborn stars, a 200,000 light-year-long contrail left behind by a runaway black hole. Van Dokkum put it simply, "We think we're seeing a wake behind the black hole where the gas cools and is able to form stars. Like the wake behind a ship, we're seeing the wake behind the black hole. What we're seeing is the aftermath, a ship's wake. Except the ship is invisible, weighs as much as 20 million suns, and the ripples it leaves behind are stars." At the time, in 2023, this was a hypothesis, a candidate explanation, carefully labeled as such. Nothing like it had ever been seen anywhere in the universe. But if it was true, it would confirm a prediction that astronomers had been quietly carrying around for about 50 years. Because here's the thing. Scientists had long suspected that black holes could, under very rare circumstances, be thrown out of their galaxies. They had just never caught one doing it. To understand how you evict the heaviest object in a galaxy, we need to talk about what supermassive black holes actually are and where they live. Most large galaxies have one. A single, enormous black hole sitting at the exact center, sometimes weighing millions or even billions of times more than our Sun. Our own Milky Way has one. These giants dominate their galaxies with their immense gravity. Everything else arranges itself around them. And whether these anchors can ever escape their tight galactic bonds has been a long-standing mystery, one that matters far beyond this single object. Because galaxies and their central black holes grow up together. Studying how one of these giants gets torn loose tells scientists something fundamental about how galaxies and black holes have evolved across the history of the universe. So the idea of one of these anchors being ripped loose sounds absurd. In Van Dokkum's words, the forces needed to dislodge such a massive black hole from its home are enormous. And yet it was predicted that such escapes should occur. For roughly 50 years, this idea lived purely in the realm of theory. Here's how the theory works. It starts with a collision. Galaxies merge. This is normal. It happens multiple times over the lifetime of a single galaxy. A galaxy the size and mass of the Milky Way has experienced several such mergers during its lifetime. When two galaxies merge, each one brings its own supermassive black hole to the wreckage. And over time, those two giants sink toward the center of the newly combined galaxy, where they begin to circle one another. Astronomers call this a binary black hole, two monsters, locked in orbit, whirling around each other in a gravitational dance. From here, there are two known ways to launch one of them into the void. The first mechanism is a merger kick. If the two black holes spiral all the way in and merge into one, the collision releases a burst of gravitational waves, ripples in the fabric of space itself. And under the right conditions, that release is lopsided. The radiation carries momentum, and the newly formed black hole gets a powerful kick in the opposite direction. A kick strong enough, in theory, to reach speeds of 1,000 kilometers per second, fast enough to escape the gravity of an entire galaxy. The second mechanism is a three-body interaction. Imagine that binary pair still circling at the center of the merged galaxy. Now a third galaxy arrives, carrying its own supermassive black hole, and that third giant comes crashing into the dance. As the old idiom goes, two's company and three's a crowd. Three supermassive black holes in close quarters is a chaotic, unstable configuration. It's a game of galactic billiards, and in that game, one of the players can steal momentum from the other two and get flung out of the galaxy entirely. When the single black hole takes off in one direction, the remaining pair recoils and shoots off in the opposite direction, like the two sides of a slingshot. And there's an extra twist to the billiards. We can't even be certain which player got ejected. The original binary pair may have remained intact and thrown out the newcomer. Or the interloper may have muscled its way into the dance, replaced one of the original two, and kicked out the previous companion. Either version ends the same way with a fugitive. Either way, the result is the same. A supermassive black hole, alone, unbound, and moving at incredible speed through intergalactic space. Now, how would you ever find such a thing? This is the genuinely hard part. A black hole is, well, black. It emits no light of its own. It's bounded by an event horizon, a one-way surface that traps everything, including light. A black hole coasting through empty space is very close to perfectly invisible. Unless the space isn't quite empty. Galaxies are surrounded by enormous halos of thin, tenuous gas. And when an object with the mass of tens of millions of suns punches through that gas at supersonic speed, the gas notices. The gas in front of the black hole gets shocked and compressed by the impact. Behind the black hole, in the wake, the pressure is lower than at the front, so gas accumulates there, settles, and cools down. And when gas cools and clumps, it does the one thing gas has always done in this universe. It makes stars, so you can't see the ship, but you can see the wake, a narrow, glowing corridor of newborn stars, stretching backward from the black hole all the way to the galaxy. It escaped from a 200,000 light-year record of exactly where it has been. And this is where the discovery becomes something bigger than a curiosity. Because star formation is one of the most studied processes in all of astronomy, and this was a version of it that nobody had ever seen. Stars igniting far outside any galaxy, seemingly born in empty space, triggered not by a galaxy's slow churn, but by the violent passage of a runaway object. The team would later estimate that the stars formed in this wake add up to roughly 100 million times the mass of the Sun. 100 million suns worth of stars, created in the emptiness between galaxies by something passing through. This mode of star formation was completely unknown before this object was found. But in 2023, one crucial piece of the picture was still missing. The wake was there, the trail was there. What the theory also predicted, based on shock models and the brightness of that glowing knot of gas, was something at the front of the black hole, a structure that had not yet been seen directly, at the leading edge, where the monster meets the gas head-on. Remember that detail. It's going to matter. When a discovery is this strange, the burden of proof gets heavy. So the team went looking for supporting evidence. And what they found was a series of quiet, unsettling details, each one small on its own, and each one pointing in the same direction. The first anomaly. The host galaxy's center appears to be empty. Every large galaxy is supposed to have a supermassive black hole at its core. But when astronomers examined the compact, star-forming galaxy at the base of the streak, they found no sign of an active black hole at its center, or at the very least, nothing actively feeding. Nothing generating the powerful jets of energy that telescopes can detect. Think about what that means. A galaxy, missing its anchor, a throne, sitting empty. It's exactly what you would expect to find if the galaxy's central black hole had been thrown out. And here's a counterintuitive footnote to that. According to Van Dockum, losing its supermassive black hole is unlikely to affect the galaxy very much at all. The stars keep orbiting. Life, galactically speaking, goes on. The real drama isn't in the galaxy left behind, it's wherever the fugitive is headed next. The second anomaly is subtler and stranger. On the opposite side of the host galaxy, directly opposite the streak, there is a feature in the data, something that might be the recoiling binary. Remember the slingshot? When one black hole gets ejected in one direction, the remaining pair shoots off the other way. If this feature is what it appears to be, then we may be seeing both halves of the same ancient catastrophe, frozen on either side of a wounded galaxy. To be clear, this is circumstantial evidence, not confirmation, but it fits. The third anomaly is the knot itself, that remarkably bright point of ionized oxygen at the outermost tip of the trail. Researchers believed the gas there was being shocked and heated by the black hole's motion as it slammed into the material ahead of it. Or it could have been radiation from a disk of matter swirling around the black hole. Van Dockum was candid about the limits of the picture. Gas in front of it gets shocked because of this supersonic, very high-velocity impact, but how it works exactly, he admitted, is not really known. And astronomers even sketched out a possible timeline for the crime. The suspicion was that two galaxies had merged perhaps 50 million years ago, bringing two supermassive black holes together at their center. Then a third black hole arrived, the configuration destabilized, and roughly 39 million years ago, one of the giants was launched into the dark. So by the end of 2023, the case looked like this. A trail of stars that shouldn't exist, a galaxy missing its central black hole, a possible recoiling pair on the far side, and a bright, shocked knot of gas at the tip of the streak, right where a fleeing black hole ought to be. All of it was consistent. None of it was proof. In science, difficult to explain any other way is not the same as confirmed. Van Dockum said it himself. All we really had was a streak that was difficult to explain in any other way. What was missing was the smoking gun. So the team applied for time on the two most powerful space observatories in existence, NASA's Chandra X-ray Observatory and the James Webb Space Telescope. And then they waited. December 2025. More than 2.5 years after the streak was first noticed, the James Webb Space Telescope turned toward the tip of the trail. Webb is unique among telescopes for its sensitivity and its sharpness. And what the team was hunting for was that missing piece of the theory, the structure predicted at the leading edge of a runaway black hole, a bow shock. Here's what that means. A boat moving through water pushes a wave out in front of its hull. A supersonic object moving through gas does the same thing. It piles the gas up ahead of itself into a shock front. If the runaway black hole was real, there had to be a bow wave of compressed, displaced gas at the front of the wake, pushed aside by the passage of the monster. The instrument Webb used for the job is worth pausing on. It's called an integral field unit, and it does something that sounds almost unfair. It observes a small patch of the sky and captures an image and a spectrum at the same time, for every point in the frame. That means astronomers don't just see the object, they can read the composition, the temperature, and the motion of the gas, all at once, across the entire field. So Webb looked. And there it was. The imagery astounded the team. Webb rendered the shock at the leading edge with unprecedented clarity. In Van Dokkum's words, "The shock signatures are crystal clear, and there is just no doubt about what is happening here." He compared it, once again, to a ship. The ship is a black hole, and very difficult to see, but we can see the water, really, hydrogen and oxygen gas that it pushes out in front of it. And the bow shock did more than confirm the picture. It let the team measure the black hole directly, because the gas at the tip of the wake is being shoved sideways at hundreds of kilometers per second, and the speed of that displaced gas is directly tied to the speed of the object displacing it. The verdict: the black hole is moving at approximately 1,000 kilometers per second. That's about 2.2 million miles per hour, roughly 3,000 times the speed of sound at sea level here on Earth. It is one of the fastest moving massive objects ever detected, and it is that speed that allowed it to break the gravitational grip of its former home. It has now traveled about 230,000 light-years from its point of origin. The team's conclusion, in their new paper, was direct. The evidence for a supersonic bow shock at the head of the trail is very strong, bordering on overwhelming. In this particular case, the researchers now believe the first scenario is the likely culprit, a black hole merger, and a gravitational wave kick powerful enough to launch the newly formed giant into the void. The research suggests the runaway was produced after at least 2, and potentially as many as 3, black holes all interacted, each carrying a mass of at least 10 million suns. The violence of that encounter, Van Dokkum said, must have been quite something. And the different datasets reinforced each other. The observations from Hubble, from Keck, and from Webb, different telescopes, different wavelengths of light, all provide different pieces of the puzzle. And in Van Dokkum's words, they fit together beautifully, exactly as predicted by theoretical models. Even so, the researcher who found it never stopped being surprised by it. "Everything about this research surprised me," he admitted. "I never expected to see such a thing, and confirming it with Webb was just incredible." One note of scientific honesty here, because this channel deals in facts. As of this recording, the confirmation paper has been submitted to the Astrophysical Journal Letters and is publicly available, but it has not yet completed peer review. The lead author has published several peer-reviewed papers on this object over the years, and the team calls this the first confirmed runaway supermassive black hole. 50 years after theorists first predicted that such escapes should occur, the prediction has, by every indication, finally been proven. When Van Dokkum was asked about it, his answer wasn't measured academic language. It was 3 words: "It boggles the mind." And he raised one more possibility, not a threat, but a thought experiment. What happens if this runaway ever encounters another galaxy? The answer? The galaxy-sized shockwave traveling ahead of the black hole would slam into that galaxy's dense gas, compressing it, shocking it, and likely igniting a firestorm of new star formation. In his words, it would be quite the show. There is one more wrinkle worth mentioning, because it shows how carefully scientists are now treading. Elsewhere in the sky sits an ambiguous object nicknamed the Cosmic Owl, 2 colliding ring galaxies, billions of light-years away, whose rings look like a pair of owl eyes. Each eye has an active supermassive black hole at its heart. And oddly, there is a third supermassive black hole sitting between the 2 galaxies, embedded in a cloud of gas. Some researchers proposed that this third black hole might be another runaway, escaped from one of the hosts. But Webb observations by Van Dokkum's own group challenged that interpretation. Their data suggest that this out-of-place black hole more likely formed right where it sits, through the direct collapse of gas compressed when the 2 galaxies nearly collided. Which, if you think about it, is its own kind of astonishing. The debate is no longer whether a supermassive black hole can be found outside a galactic center. The debate is about which impossible explanation applies. Now, here's the thing about this discovery. It didn't happen in isolation. Over these same few years, astronomers kept stumbling into objects that refused to fit not just in deep intergalactic space, but at the edge of our own solar system and in the signals washing over our radio telescopes. Consider what this stretch of time quietly produced. On May 16th, 2023, the same year the streak was found, the 2-meter Subaru telescope on Mauna Kea spotted a small, icy world in the far outer solar system. The discovery came out of a survey called FOSSIL, short for Formation of the Outer Solar System, an Icy Legacy, an international collaboration led primarily by astronomers from Japan and Taiwan. The object was designated 2023 KQ-14, and the team gave it a nickname that fits the survey perfectly: Ammonite, after the ancient marine fossil. Because its orbit is essentially a fossil itself, dynamically stable and likely unchanged since the beginning of the solar system, 4.5 billion years ago, Ammonite is only the fourth known member of an exclusive class of objects called sednoids, distant bodies whose stretched, elongated orbits never bring them anywhere near the known planets. It is somewhere between 220 and 380 kilometers across. It takes roughly 4,000 years to complete a single trip around the Sun. Its distance swings from about 66 times the Earth-Sun distance at its closest, out to more than 400 times that distance at its farthest. Even at its nearest point, which it will reach in February of 2063, it stays more than twice as far out as Neptune, beyond the gravitational reach of any known planet. Confirming an orbit like that takes patience. The team followed up with the Canada-France-Hawaii telescope in July of 2024, and then went digging through archives, where they found Ammonite hiding in old survey images from 2021 and from as far back as 2014. In total, they traced its path across 19 years of data. The discovery was announced in April of 2025, and the research paper was published in Nature Astronomy that July. And what they found was troubling in its own quiet way. The other three known sednoids all have orbits pointing in roughly the same direction, a clustering so improbable that it inspired the famous Planet 9 hypothesis. The idea, proposed in 2016 by Caltech astronomers Konstantin Batygin and Mike Brown, that a hidden giant planet is shepherding these objects with its gravity. As Brown once wrote, "The signs in the sky were clear. Something was out there." Ammonite's orbit points the opposite way. Simulations suggest that a planet on the commonly predicted orbit would likely have ejected Ammonite entirely. One of the researchers, Yukun Huang of the National Astronomical Observatory of Japan, put it plainly: the fact that Ammonite's current orbit does not align with those of the other three sednoids lowers the likelihood of the Planet 9 hypothesis. If the hidden planet exists, it may orbit farther out than expected, perhaps around 500 times the Earth-Sun distance. Or stranger, still a planet may once have existed in our solar system and was ejected long ago, leaving these orbits behind as its only fingerprint. There's even a hint of when. Simulations by the team suggest that around 4.2 billion years ago, roughly 300 million years after the solar system formed, all four sednoids may have shared a common alignment, a primordial clustering that has since slowly drifted apart. The statistical confidence is over 97%, suggestive, not conclusive. And to be fair, not everyone agrees the hypothesis is in trouble. Batygin himself has argued that Ammonite sits below the distance threshold where his models predict clustering should occur at all, and that the Planet 9 theory can comfortably accommodate this new find. Some astronomers question whether the clustering was ever real to begin with. The debate is genuinely unsettled, and with the Vera Rubin Observatory now scanning nearly the entire southern sky every few nights, All of these hypotheses will soon face rigorous observational tests. But notice the shape of the idea at the center of it. A massive object, possibly ejected from its home, betrayed only by the trail of evidence it left behind. Sound familiar? And then there are the signals. Since 2005, radio astronomers have been puzzled by a class of objects called long-period radio transients, coherent bursts of polarized radio waves that repeat on timescales of minutes to hours. That might not sound strange until you remember what usually makes pulsed radio signals: pulsars, spinning neutron stars that flash tens to hundreds of times every second. These new signals pulsed thousands of times slower than that. Some would switch on, burst for a while, and then vanish for hours in some cases, weeks before returning. Current models suggest neutron stars rotating that slowly shouldn't be able to produce such signals at all. Only about a dozen of these objects have ever been found, and for 2 decades, their origins remained unclear. Then, in research published in Nature Astronomy, in June of 2026, a team led by a PhD student, Covey Rose of the University of Sydney, finally pinned one down. The hunt itself is a small detective story. Using Australia's ASCAP radio telescope, the team searched a survey of roughly 3 million radio sources for the rare handful that were highly circularly polarized, a signature of strong magnetic fields. Only about 100 sources made the cut, and only one of them had no known astronomical identification at all. That one became ASCAP J 1745-5051. The team refined its position with the Meerkat telescope in South Africa, matched it to a faint star in optical data, and then threw nearly everything at it: optical telescopes in Chile and space observatories watching in ultraviolet and X-rays. What emerged was a portrait of a violent little system. A white dwarf, a dead star, roughly the size of Earth, but with a mass close to that of the Sun, locked in a 4-hour orbit, with a red dwarf companion of about 1/10 the Sun's mass. The two stars circle each other so closely that the white dwarf is actively tearing material off its companion. Astronomers call systems like this cataclysmic variables. As Rose put it, "For the first time, we have pinpointed the origin of these signals, confirming the source to be an accreting white dwarf star. The stolen, infalling matter heats up and produces X-rays. The clashing magnetic fields of the two stars, interacting with that charged material, generate the tightly beamed radio bursts. Both signals repeat on the same 4-hour cycle, the orbital period of the binary. But here's a telling detail. The radio and X-ray signals don't peak at the same time, which tells us, in Rose's words, that they're being produced in different regions of the system. And buried in the radio pulses, the team found something almost poetic. Fine, narrow interference patterns in the signal structures previously seen clearly in only one other place in the entire universe. The interaction between Jupiter and its volcanic moon Io, right here in our own solar system. A pattern first studied on a planet next door, now echoed by a dead star devouring its companion far across the galaxy. This was only the second long-period transient ever seen, producing regular X-rays, and the first where the cause of that regularity was confirmed. As Professor Tara Murphy of the University of Sydney noted, similar objects had been linked to binary systems before, but this was the first where both stars and the accretion process could be clearly seen in action. Rose called the system a stellar Rosetta Stone, a key for decoding all the other mysterious signals like it and for determining whether they are more like pulsars or more like this: two stars locked in a magnetic embrace. These systems, he said, are natural laboratories. They allow us to test how matter behaves in magnetic fields and gravitational forces that could never be recreated on Earth. 3 discoveries: a black hole that left its galaxy, a frozen world that undermines a hidden planet, a 20-year-old radio mystery that turned out to be 2 stars locked in a magnetic embrace. What do they have in common? In each case, the object itself was nearly invisible. And in each case, we found it anyway by reading its wake, its orbit, its signal, the evidence it couldn't help but leave behind. Our instruments have crossed a threshold, and the universe, it turns out, has been much stranger than our catalogues the whole time. So let's return to the runaway, because it leaves us with a question that is easy to state and very hard to answer. How many are there? Galaxy mergers are common again. A galaxy like our own has been through several, which means binary black holes should form regularly throughout the universe. What we don't know is how often those binaries merge and how often the resulting kick actually removes a black hole from its home. Depending on how the collisions are modeled, the population numbers vary. Van Dokkum's view is refreshingly empirical. Now that we know how to look for them, we can find other examples, and then we can answer the question directly from data by counting the number of escapes. Here's what the data suggests about how that search will go. These wakes are thin, so thin that from the ground they blur beyond recognition. You need space-based imaging to see them. Fortunately, wide-field imaging with Hubble-level quality is just around the corner, with NASA's Nancy Grace Roman Space Telescope and, slightly blurrier, the Euclid Mission Survey telescopes designed to sweep the whole sky rather than stare at one point. Finding thin streaks in that ocean of data may require machine learning algorithms that are very good at spotting one specific weird shape in a sea of everything else. In other words, the first runaway was found by a human being, by accident, in an old photograph. The next ones may be found by machines, on purpose, by the thousands of square degrees. And that census, Van Dokkum said, will tell us how often this happens, something we dearly like to know, and that is where this story leaves us. Not with an answer, but with a census that hasn't been taken yet. Somewhere between zero and many, there are invisible giants coasting through the dark between galaxies, each one carrying the mass of tens of millions of suns, each one pushing a galaxy-sized shockwave ahead of it, each one perfectly silent and perfectly black. For 50 years, they existed only in equations. Then one of them left a trail. Think about how close this came to never being noticed. The photograph sat in an archive. The streak was dismissed, at first glance, as a scratch on the detector. One astronomer, looking for something else entirely, decided the little flaw was worth a second look, and that second look confirmed a half-century-old prediction about the most extreme objects in the universe. Van Dokkum described what that feels like from the inside. Much of what we do, he said, is hypothesis testing or refining previous measurements. But sometimes there is this bolt out of the blue, a completely unanticipated discovery. That is rare, but it is the best. Every answer brings another question. That's how science moves forward. We now know that galaxies can lose their anchors. We know that stars can be born in the emptiness between galaxies, in the wake of something passing through. And we know that our maps of the sky are not finished, that they may never be finished. Somewhere out there, in the dark between the galaxies, an invisible monster is still running. And the only reason we know it exists is that for 200,000 light years, it left the lights on behind it.